Now before you click away, this problem is probably one of the most satisfying problems you're ever going to see. It looks very complicated on the face of it, but if you give it a quick 1 minute or so read, you'll probably be able to work out what you might want to do to start. Now I promise this is going to be a very satisfying problem, and let's get into the solution. So first of all, what we should realize is f of n is actually a second order recurrence relation, which means we can solve it quite easily. So that should be our first step. Then once we solve it, we're going to input it into here, and then our goal is going to be to try show us a rational number, which is actually going to be simpler than you might think. So first of all, what let's do is rearrange this equality to get it in the form of a standard second order recurrence relation, like so. We get an auxiliary equation of this, and well, this tells us that our roots are a half or 2. I'll leave you to check that yourself. This then suggests that the general term of f of n is c1 a half to the n plus c2 2 to the n. And then taking our initial conditions, this gives us 0 equals c1 plus c2. And taking our other initial condition, f of 1 equals 3 over 2, that's going to give us that 3 over 2 is equal to c1 over 2 plus 2c2. We're now rearranging the top one, we get c1 as minus c2. That tells us that 3 over 2 equals minus 3 over 2 c1, and so c1 is equal to minus 1. And hence c2 is equal to 1. That's quite nice, because what we've been able to do then is being able to show that f of n is equal to 2 to the n minus 1 over 2 to the n. Well, I've just rearranged a half to the n as 1 over 2 to the n instead. Okay, so now that we've got our general term for f of n in terms of n, let's input it into our sum. I'm also going to change this notation because it's quite disgusting. I don't know who decided to put an n greater than 0 here. So we're going to write this as n equals 0 to infinity of 1 over f of n, or f to the 2n, sorry. We can then replace this. So we get 1 over 2 to the 2n minus 1 over 2 to the 2n. Now there are two options you can do, and I'll leave the second option as an exercise. So option 2, what you can do is you can divide top and bottom and bottom by 2 to the 2n, or well, minus here. This is going to leave you a sum of a geometric sequence. And then what you're going to do is, instead of writing that sum, just put the geometric sequence back. And that's got a really satisfying solution, but it requires a little bit of number theory knowledge. Okay, anyway, we're going to do an even better way though. We're going to multiply top and bottom by this. So that's going to give us the sum from n equals 0 to infinity of 2 to the 2n over 2 to the 2n squared minus 1. Now, the astute watcher would realise that this is a bit like x over x squared minus 1, where this is x. Now, why is that useful? Well, if we're doing a sum like this, we'd probably assume there's some sort of telescoping, whether it be from partial fractions. Unfortunately, it's not in this example. So partial fractions, or some sort of polynomial division or polynomial manipulation. Now, for this example, what you want to realise is that we factorise the bottom, like so, and then we can add and subtract 1. Like this. Where what I've done is, when subtracting the 1, I've replaced this with its original form up here. Now this cancels, and that's going to leave us with 1 over x minus 1 minus 1 over x squared minus 1. Now the reason we've done this is because x is 2 to the 2n, and hence x squared is 2 to the 2n squared, which by the multiplication rule is 2 times 2 to the n, and we can bring that 2 in. So in other words, we're probably going to get a bit of telescoping here. So this is kind of like the nth term, and then this is going to be the n plus 1th term, and then that's going to cancel out the next term. And that's the idea here. So what seemed like a complicated number theory question where we're going to do a classic rational irrational proof, assuming it's P over Q, getting some sort of contradiction. Instead, we're actually just going to directly calculate the sum, or hopefully directly calculate the sum. And then fingers crossed this is going to be an obviously irrational or rational number. So let's replace our findings into the sum. So we've got a sum from n equals 0 to infinity of 1 over 2 to the 2n minus 1 minus 1 over 2 to the 2n plus 1 minus 1. Now if you write this out term-wise, for n equals 0 we get 1 over 2 to like this, minus 1 over 2 to the 2 to the 1 minus 1, plus 1 over 2 to the 2 to the 1 minus 1, minus 1 over 2 to the 2 to minus 1, so on. And what we realise is that that is going to cancel that, and hence the next term, that is going to cancel whatever comes next. And so we're going to be left with sort of a limit that then goes to infinity of 1 over 2 to the 0 minus 1. And then we're going to have a term that gets discarded, of 1 over 2 to the 2n minus 1. But clearly this goes to 0. So we're going to be left with 1 over 2 to the 2 to 0 minus 1, which is 1 over 2 to the 1 minus 1, which is 1. So in other words, yes, this is rational. It's just 1.